Great. So we are very glad to have Noah Olander from Columbia, and he's going to tell us about semi-orthogonal decompositions and dimension.
Great. Thank you very much for the invitation. I'm excited to speak. So I want to talk today about a theorem just about, if you have some variety which appears in a component of a semi-orthogonal decomposition of another variety, I just want to prove that the dimension of the sort of sub thing is at most the dimension of the big thing. All right, so let me say clearly what I mean. So throughout the talk, X and Y are just going to be smooth projective varieties. Over some ground field K, which is totally fine if you assume it's the complex numbers. And when we have a smooth projective variety, you can look at the bounded derived category of coherent sheaves on X. So that's the same thing as the bounded derived category of the abelian category of coherent OX modules. And this is so it's a K-linear triangulated category. So K-linear just means that the HOMs in this category are naturally K vector spaces. Okay, and so we'll be talking about a lot of functors between such categories, and I'm always going to assume that they respect these two structures on the category. So all functors are going to be exact and K-linear.
So maybe to get this out of the way early, I'm guessing that people aren't going to need to know precisely what a triangulated category is to follow what your talk is, I think, right? So, I mean, it'll help to,
yeah.
So, I mean, are you going to say that they're basically complexes of coherent sheaves up to roughly, or how to think about it so people?
That's yeah, so that's a good point, yeah. So, yeah, so the objects of this category, right, are they're bounded complexes of coherent OX modules, right? And we sort of think of them up to quasi-isomorphism. And I guess I'll probably be able to say a little bit more about the HOMs in this category, but I think a really important thing is that you have, so if you have a coherent OX module, you can sort of look at that as a one-term complex. And by doing so, you get just a fully faithful embedding of coherent OX modules inside of the bounded derived category. So, I mean, whenever I take an object of the bounded derived category, you should probably, like a good example is just a module. Yeah, and yeah, please, yeah. So if I say something, yeah, that doesn't make sense, yeah, please ask. Yeah.
So it sounds so the way you're thinking about it is,
yeah.
We all like vector bundles, we all like coherent sheaves,
Mm-hmm.
And then this is like complex of coherent sheaves to first approximation. For some reason, it captures lots and lots and lots of surprisingly much
Great.
the variety itself you're saying, and then
yes,
whatever this category is, and it's like, okay, great. And
great.
Morphisms are weird, you already said.
Morphisms are weird,
like,
yeah. And then there's this triangulated structure which we're definitely going to get into in a moment, and I'll sort of be talking about cones and stuff, and maybe that'll be a good time to review. Yeah,
great.
Okay, so let me just state what I want to prove. So so if there exists a fully faithful functor, so f from dbco of x to dbco of y, then the dimension of x is at most the dimension of y. So if you're thinking about coherent sheaves, I mean, okay, so for example, this implies that there's no, fully faithful functor of abelian categories from the category of coherent sheaves on X into the category of coherent sheaves on Y. And probably, this seems very almost obvious maybe, because, how could you possibly put like a bigger category into a smaller one? And indeed, people kind of expected this to be true for a long time. So the other thing I want to talk about today is this.
I'm sorry, but before you move on, So I guess one way to get a fully faithful embedding would be if X is a closed subscheme of Y and you take capital F to be the push forward map.
Okay, that's a good question. So that gives you yeah, you're totally right. That's a good point. Yeah, so that's not a fully, yeah. So
could you explain why that isn't a fully faithful embedding and give an example of a fully faithful embedding?
Sure. So okay, I do plan to give like a list.
Oh, sorry, maybe I'm jumping ahead.
No, that's good. I do plan to give a list of some, some important fully faithful functors in algebraic geometry. But yeah, you're totally right. I wanted to make a coherent statement about the category of coherent sheaves, but I shouldn't have quite said that. Yeah. So maybe stay tuned, and I'll give some examples of common fully faithful functors between derived categories.
Staying tuned.
So, okay, the other thing I want to talk about today is this. So it's this conjecture of Orlov's conjecture. So it's simple to write down in equations, but it's going to take a little bit longer to describe. So Orlov's conjecture just says that the Rouquier dimension, so this is something that I have to explain what it means, of the bounded derived category of X is equal to the dimension of X. So this is called the Rouquier dimension. And it's some invariant of the triangulated category. Okay. Right. So my plan for the talk today is sort of to try to explain what the Rouquier dimension is, explain sort of what Orlov's conjecture means, and maybe say some cases that we know Orlov's conjecture to be true, and also explain why it implies the theorem.
So basically you've got this category, this derived category, and you should be able to recover lots about X, and in particular its dimension, and there should be somehow I don't know, like there's a thing like something, yeah, great. And so and Rouquier's got this candidate dimension and Orlov is saying that's the correct, that will recover it.
Absolutely, yeah, right. So some people would say that like a non-commutative algebraic variety is some sort of like triangulated category or DG category, satisfying some properties. And this kind of Rouquier dimension, it gives you it's a good proposed way of recovering, it extends the definition of dimension from the commutative to the non-commutative case or something like that. Yeah. So yes. Okay. Right. Oh, and yeah, so my plan, yeah, I was worried that I cut out for a little bit there. I don't know if I did, but yeah, so my plan is to sort of explain why this conjecture was known to imply the theorem. And I kind of want to do that because so first of all, the conjecture is amazing. And I think that we would I hope that someone proves it. And the second reason is that my proof of the theorem is sort of to prove a softer version of Orlov's conjecture. And it'll be kind of clear in what way it's analogous to Orlov's conjecture, the thing that I try to prove. Okay, so let me first discuss. So I have to tell you what Rouquier dimension is, and unfortunately, it's going to take a little bit of work to say what that is. So we have to talk about generation time for triangulated categories. So here's where we're going to talk about sort of what are the operations that you have on a triangulated category. So okay, so in this part, let's say T is a triangulated category. Okay, it's a generalization of, okay, so the bounded derived category of coherent sheaves on a variety is an example of a triangulated category. And this means that it has sort of shifts and something called a triangle, which is they sort of come from short exact sequences of complexes. Okay, and I'll sort of get to that. Okay, but what I want is to take some subset of the objects of T. And then I want to think about how we can build all the objects of T from S using the operations that sort of come with the structure of a triangulated category. So we're going to build objects of T from the objects which live in S using some operations. Of the following type. So first, you have these operations which are shifts. So this corresponds to just sort of shifting a complex of coherent sheaves, taking finite direct sums, and extracting direct summands. Okay, so these are all operations which make sense on a triangulated category. So what I want to say when I'm talking about generation time is these operations we're sort of not going to keep track of. So a nice way of saying that is that we're gonna count these operations as sort of being free. Anytime you can build something using a shift or a direct sum or a direct summand, we don't keep track of that. It doesn't cost you anything. Okay, and then so that finally the kind of interesting operation that we're going to look at is taking extensions or cones is another way of saying it. So given a distinguished triangle, so A to B to C to A shifted by 1. Okay, so this is part of the structure of a triangulated category is that we have certain diagrams of this form which we call distinguished. And in the case of in the case that T is the bounded derived category of a variety, they basically come from when you have a short exact sequence of complexes. So A, B, and C in that case are all represented by complexes, and you can get a triangle by having a short exact sequence of complexes from A to B to C. Okay, but you can have some more triangles too. Okay, so given a triangle like this, we're going to declare that it costs $1, okay, to build B out of A and C. Okay. So this is sort of the important operation that we're going to keep track of when we're talking about generation time. All right, and so given this, I'm going to just write, so there's this notation. So it's sort of the subcategory generated by the set of objects S in n+1 steps. And that's the objects built from S. Sort of using, okay, which cost at most $n to build. Okay, so these are sort of things that that you can build using at most n cones. That's like the very quick way to say it. Any questions about the definition of this subcategory? So I'm definitely going to give some.
So I have a toy, right? Great. So I have a toy model in my mind, and maybe this is helpful for people who are seeing these for the first time, with just modules over a ring, where you have, I know what free modules are, and we're talking about complex, so shifts I'm paying no attention to, and direct summands of free modules I find are, weird, but I'll take them for free since you're giving them to me. And now you're telling me I can extend things and try to get modules in this by extensions, and every finitely generated module has a price, I guess.
Right. Yes.
And you're telling me that, great, okay.
Right,
And so,
yeah.
So to be totally concrete, if I look over, let's say a DVR, I can buy every module for $1?
Yeah, so if you start, okay, but depending on what you start with, right? So you have to
Oh, so
say what you
starting,
start with.
starting with free things, starting with
Yeah,
free
so
things.
starting with R, of course, yeah, you can build like all the finite free modules for no money, right? And then exactly, so you have, so every module has projective dimension 1 and then, or at most 1, right? So you can build everything using sort of 2 free modules and a cone.
And then
Exactly.
and then the Hilbert resolution thingy for whatever you call it, Olander book spot, whatever. The
Great.
module over a regular local ring of dimension n said you have a free resolution up to
Great.
n, and you're going to tell me that therefore all generalizing Jesse's statement, every finite
Great.
module costs at most $10 for something in dimension n, and now you're making a strong case for dimension, that being dimension. Oh, there we have
Absolutely.
Jesse said smooth DVR, so that now we have smooth things. So now, or regular things, right? Okay,
Right.
great.
Great. Yeah. Okay. So you're both totally anticipating examples, which is awesome. So yes, those are awesome examples. Yeah. So it's related to like the projective dimension of a module. So yeah, how much does it cost to build the module using R? Yeah, it's totally related to the projective dimension of that module. Okay. And so finally, I want to say what the Rouquier dimension of T is. So it's the inf of all the set of integers such that there exists a single object such that you can build everything out of this one object using D steps. Sorry, equals T.
Oh, so your starting point. Okay, great. So in this case, Betsy and I are thinking about starting with the ring itself, whereas possibly there's some other module.
Right.
I've already speculated, or Macaulay, maybe the dualizing module. I don't know, some God-given module out there from which you can very cleverly do something similar.
Perfect.
That's beyond my my pay grade to guess what that might be.
Exactly. Right. So this is an interesting thing about the Rouquier dimension. It's hard to give lower bounds, because how can you prove that, like, you've picked a really good generator which generates the derived category in a small number of steps, but it's quite hard to prove that nobody could give you another object that would do it better. Yeah, so this is sort of an intricate thing about the Rouquier dimension. Okay, and I also want to say, of course, that so given an arbitrary T, it's not obvious at all that the Rouquier dimension is going to be finite. So RDim T equals infinity is very possible, and it happens a lot. Okay, but in our case, where we have a smooth projective variety, we actually have the following very nice bounds. So we have dimension of X is less than or equal to the Rouquier dimension of dB co of X. And we know also that it's finite and less than or equal to twice the dimension of X. Okay, and this was proved in Rouquier's original paper where he defined the Rouquier dimension. Okay, and just to remind everyone, so Orlov conjectures here that this is actually an equality. Okay, and then this one, so this was proven in this amazing paper by Bondal and Vandenberg.
And that's because they somehow very cleverly give a generator.
Exactly, yeah. They have a really nice argument. Yeah.
Oh, so it's not like a generator. You can't just say it in like 5 words and suddenly we're like, yeah.
Yeah, you're right. You sort of can. I mean, it comes from taking a resolution of the diagonal by box products, and then you sort of take a sum of all of those box factors. And it's really nice to see why that's a strong generator, or why that gives you this upper bound. Yeah. Okay. So I want to now give
on X.
Yeah. So at the beginning, yeah. Thanks for pointing that out. So at the beginning, I just was saying, let's just have everything be smooth and projective over some base field K.
Thanks.
Mm-hmm. Right. Okay, and now I want to actually give some examples, which have been anticipated, so they should be a little bit easier to explain now. Okay, so all right.
Are
So
there
if you,
inequalities known if it's not projective?
that's also a good question. So yeah, so in the affine case, it's known. Something that I'm gonna try to explain the proof of today is gonna show that it's also true for the quasi-affine case. But in general, we don't know too much. In general, I think like we don't even know. It's hard to prove like for a general smooth projective variety that the Rouquier dimension is actually less than twice the dimension. So in general, we know very little.
But sorry, did you say the lower bound is known in the quasi-affine case?
Yeah. Sorry. So we know that. Okay. So actually, Orlov conjecture is equal here even for x quasi-projective and smooth. And we know that for when x is affine, we know it when x is quasi-affine.
Very cool.
Mhm.
So one more question. Do you know if there's counterexamples when it's not projective? Like if it's say like a complete variety that's not projective?
That's a good question. I don't know why we would expect there to be.
Sure.
And I'm gonna explain today some sort of so I'm gonna prove some weaker version of Orlov's conjecture for all smooth projective varieties, and actually that is even true for if you just have like a smooth proper algebraic space over a field, this analog. So it's really unclear to me if you could make a counterexample like using something which was complete but not projective. Yeah, it would be awesome that.
Sorry, I didn't quite understand the last comment about you're saying there's something about the Orlov conjectures being used for algebraic spaces. Sorry, could you just repeat that?
I'm gonna explain a weaker version of Orlov's conjecture today, and that thing will be true in the proper case. And like
wonderful.
you won't even just
okay,
smooth
I won't
proper
hold
thing.
you to that. Just thank you.
Right. Thanks.
Is there anything short and enlightening one can say about the lower bound? Because it seems like somehow that's actually the more explicit, the less explicit of the two bounds here, Rouquier's original result.
So like, are you asking like how would one try to prove a lower bound like that, or? Yeah. So okay. He sort of reduces to kind of a local thing. Like, so, I mean, the ultimate calculation is that if you have, like a local ring, and you know that, okay, maybe you have a regular local ring or something, then he actually of dimension d. Then what he proves is that you can't build the residue field R mod M using sort of less than d+1 steps from R. Okay, so that's like the first kind of key lower bound. So we were talking earlier about how if R mod M had projective dimension d, okay, we were talking earlier about how if R mod M had projective dimension d, then you could build it using $d from R. But there's this thing called the ghost lemma or something, which is it's really awesome, and it's a method for proving lower bounds like this. I kind of wish I could get into it, but I think I won't have time. But so this is sort of the key case, I guess.
Maybe at risk of risk of throwing more sand in the gears, right? So it sounds like presumably there's some cohomological, like there's some cohomology group is non-zero of that, and you end up proving that anything you can buy with $n has only the only possible non-vanishing cohomology group is up to n. And
Great.
that means you as soon as you produce something with a cohomology group that's non-zero costing D dollars, that means there's something that you need at least.
Right.
Exactly.
Exactly. You're going to have to provide, yeah, you're going to have to find some invariant of all the things which live in this category R sub D, and then show that R mod M doesn't have that, right? And it's a vanishing sort of thing. It's about X vanishing, of course. Yeah. Great. Okay. So yeah, let me try to just give sort of two examples where we more or less understand the Rouquier dimension. So let me take R to be a Dedekind domain. So a PID or a DVR or something, if you like. Okay, so then what we can show is that DB of the category of finitely generated R modules can be built from R using using $1. Okay, there's this annoying thing that there's a discrepancy between the number of dollars and the subscript, but okay. And so that implies that the Rouquier dimension of this category is at most 1. Okay, and you'll need to, yeah, so you would also, of course, have to prove that 1 is sort of the best you can do. Okay, but since we sort of already discussed it, let me say.
So, and if I understand how the game works, it's getting the lower bound is always harder than getting bound on the Rouquier dimension, or usually harder.
So okay, if R is a finite type over a field, then it's known by this paper of Rouquier that the lower bound is actually equal to 1.
Okay.
So it's subtle, definitely, but we actually have more. I mean, we have open questions about the upper bound, right? So Orlov's conjecture is sort of about the
great,
upper bound
thanks,
because we have an optimal lower bound. Yeah, thank you. So let's take an object K
So if you,
sorry.
So if you believe Rouquier's conjecture is true, the challenge is to write down a suitable G and then prove that you can buy everything from G using N dollars.
Perfect. Yeah, that's exactly right. Yeah. Okay, so let's take an object K of this category. So, okay, so if you have a general object, so since we know that X2 vanishes over this ring R because it's a regular ring of dimension 1. Okay, so something really fun that you can read about in Huybrecht's book on Fourier-Mukai transforms is that actually this means that in the derived category, K is very simple. It's just a direct sum of shifts of its cohomology sheaves. I should say modules, right? So a really fun thing in a triangulated category is that you have sort of, or in DB-Co of something, is that you have these sort of obstruction classes for splitting a complex as a direct sum of its cohomology sheaves, and they sort of start in X2. So anytime you have like a one-dimensional thing, it just is a sum of its cohomology sheaves. So actually, it suffices to show that that this abelian category, so just the category of finitely generated R modules, can be built from R using 2 steps, because you can build an object from these guys for free. So these are all finitely generated R modules, and you build K by shifting and taking direct sums. Okay, so so let's just take a finitely generated R module M. All right, so and this is this thing about projective dimension that we've already talked about. So M has a resolution so you first take a finite free module and you can surject onto M, and then since R is a regular ring of dimension 1, we know that the kernel is actually a finitely generated projective module. All right, and in particular, it's a direct summand of some finite free module. All right, so this is sort of where we're seeing that it's important that I said that direct summands are also free, right? Sorry, free as in they cost $0, not free as in they're free, right? So so this is actually an example of a triangle, right? In this category, because it comes from short exact sequences of complexes, if you like, but they just happen to be one-term complexes. So okay, so we built M out of R using $1. So okay, so then we're done. So any questions about this example? This is sort of $0. This is $0, and then to build the extension or the cone is $1.
So maybe for people seeing cones for the first time, derived categories, you're just saying it costs you $1 to build something with an exact sequence. Like, you know, everything else in the exact sequence.
Great.
Okay.
Yeah, thank you. Yeah. Okay. And I just want to, yeah, okay. So I want to contrast this. I want to say what happens. Like, so this was sort of a smooth affine curve. What if now you have a smooth projective curve? So this is sort of this is one of the cool examples where we actually know Orlov's conjecture to be true. Okay, so in this case, what Orlov does, okay, so I should say so Orlov proved his own conjecture for a curve, and that's what inspired him to make the conjecture for all smooth projective varieties. So you take a line bundle of degree at least 8 times the genus of X, and then what he proves is that dB_co of X can be generated using this interesting generator. So L inverse plus O plus L times L using 2 steps. So yeah, so one cone, it costs $1 to build this thing, to build any object of the derived category using this very specific generator.
And I guess one thing you see here that I hadn't fully processed is that because you're allowed to pass to direct summands, the fact that you're dealing with only one object isn't that significant, because if you have a finite collection, you just take the direct sum of them.
Exactly. Yeah, yeah, that's a great point. Yeah, right.
Thanks. I hadn't processed. That's really important, but I hadn't processed that. And are you going to say how eight? I guess I haven't seen this bound 8 times the genus appear before.
Actually, Jesse, could you say your previous question before? I was tuned out because I was typing in Discord.
Oh, sorry. So one thing I hadn't processed is that we're just looking at what happens if you start with one object and try to build everything. It's not that significant that we're only doing one object, because if you have a finite collection, you can take their sum and you're allowed to pass the summands for free.
Great. Yeah. So yeah, exactly. And another way of saying that, right, is I could have also written like the set, right? I could have taken a finite set of generators, and this would mean the same thing, right? So this would be the same thing. Great. Oh, and did you had a second question, right?
Oh yeah. So the second question was the 8G. What's the significance of that? I haven't seen that type of bound appear before.
Okay. Yeah. Actually, yeah. Let me say a word about that. So, yeah. So okay. X2s also vanish in this category, and that's used in the proof. So again, you sort of reduce to showing that the abelian category of coherent sheaves is contained in this, right? And then it's a smooth projective curve, and you have a lot of things you can use, right? So if you have a coherent sheaf, it's the sum of a vector bundle and a torsion sheaf, so you can sort of deal with those separately because direct sums are free. And then if you're working on this vector bundle part, you're also sort of allowed to use the Harder-Narasimhan filtration. And so I just want to say like one thing that goes into it. So so just one ingredient, just to give you an idea of the flavor of Orlov's proof. which is really, really cool, is so he proves that if you have if you have a vector bundle and the smallest slope that appears in its Harder-Narasimhan filtration is at least 4 times G, then you can get sort of a nice resolution for E just using O and L inverse. So then there exists an exact sequence that's like L inverse to the plus A to O to the plus B to E. And it's exact on the right, but not necessarily on the left. Okay, so this is sort of where the 8G comes in. And the thing is that you have these nice, like if you know something about the slope of the slopes of the vector bundle that you're working with, then maybe you can get some uniform way of resolving it. Okay, so this is one ingredient, and you also have to deal with the part that's the part of the Harder-Narasimhan filtration that's sort of less positive, and you do that in a different way. You sort of resolve it on the right with these 2 positive things. So it's a really cool argument.
If are you allowed to take arbitrary direct sums for $0 and arbitrary direct summands?
That's a good question. So no, you're not, but there's a variant which is used sometimes in the literature where you are allowed to do that, and that can be useful also. But in this talk, you're not allowed to do that. Good question.
Maybe it's a silly question, but if you are allowed to do that, then why can't you take like the sum of? Okay, never mind. I think I see.
Yeah, right. So you could take the sum of all the objects or something like that, right? And then and then the Rouquier dimension would be 0. Yeah. Right.
I guess if we're working in bounded in DB co, maybe that's not like allowed. But
yeah, right. Yeah.
But yeah.
Could you just say what the superscript is on the direct sum of the O's in the middle?
Oh, sorry. It's just some integer. Sorry, I just wrote a B.
Okay.
Yeah.
I always thought that was infinity, and I was like, what's happening?
Right, that wouldn't be allowed, right? Okay, yeah, all right. So I think that this is really like awesome, and it gives. So I feel that if someone proved Orlov's conjecture, it would actually tell us a lot just about coherent sheaves on a smooth projective variety, because like the proof for curves uses so much of what we know about it. So I think that we would really learn a lot if we could prove this conjecture of Orlov. So that's one of the things that I think is really exciting about it. But on the other hand, I want to stress that you need some things about like uniform vanishing of cohomology groups or something like that to sort of resolve everything in the same way.
And
Okay.
Could you say a word or two about how you handle torsion?
Yeah. So that's another thing that you have to do, right? And I think yeah. Okay. So if you have like a torsion sheaf T, then you're I think also going to resolve it like so. First of all, it's globally generated since it's a torsion sheaf, so you're going to take. I think this one has a resolution sort of going in the same direction. Like also, sorry, I wrote A again, but maybe different integers. So I think it's also going to be true that you're going to have a resolution like this for any torsion sheaf, and that also has to do with the fact that you chose L to be sufficiently positive. Yeah, sorry, I don't totally promise on this part, so you should probably look at Orlov's paper, but I think that's how it works. Okay, great. So yeah, okay. So I just want to say then that okay, so it's a lemma that if you have you have a fully faithful functor of triangulated categories, which has a left adjoint, L, then the Rouquier dimension sort of doesn't go down. So Rouquier dimension of T is less than or equal to the Rouquier dimension of T prime. Okay, and the idea is that this left adjoint is sort of it's a projector onto the subcategory, which is the essential image of this fully faithful functor. So L is like a projection back onto the subcategory. And what you do is you take a generator for T prime and you just project it down to T. Okay, so I guess all I want to say now is that this is why this is why Orlov's conjecture would imply the theorem that I want to prove today. Okay, and yeah, so this thing about the left adjoint, it turns out if you have a functor between dB_co of smooth projective varieties, it turns out that these always have adjoints by some work of Bondal and Vandenberg. Okay, so any questions before I move on? Okay, and yeah, let me give at least one example of some fully faithful functors that appear in between derived categories, since I kind of messed up in the beginning. So so if you just have, let's see, so again, X and Y are going to be smooth projective varieties, right? So if you have a morphism of smooth projective varieties, which has the following condition. So RF lower star of OY is equal to OX. Then LF upper star, it turns out, from dB_co of X into dB_co of Y is fully faithful. So this is a common source of examples of fully faithful functors between derived categories.
I'm sorry, and could you remind us when the condition RF push forward is equal to OX holds?
Right. Thanks. Yeah. So the condition RF lower star OY equals OX. I mean, so it means two things. It means that, so one is that the morphism from OX to F lower star OY is an isomorphism, and that two, there are no higher direct images of this of OY.
So for example, a family genus zero curves over a pretty general base would work?
Great, yeah, so right. So also like, yeah, right, a projective bundle would work, right? And another really key example is like if you have a blowing up in a smooth center, then this condition holds. So, okay, and the thing is that anytime you see some examples in the literature of like of semi-orthogonal decompositions, that sort of means that there's like a fully faithful functor somewhere. Okay. So just, yeah. So the proof of this is not very hard, but maybe I won't do it just in the interest of time.
And could you say a word or two about what the operation L F upper star is?
Right. So this is okay. So this is it's the left derived functor, right, of the pullback from coherent sheaves on Y to coherent sheaves on X. So what that means is that you have to represent a complex in here by a bounded above complex of flat OX modules, OY modules, and then I'm on the wrong side. Okay, so you take a complex in dB_co of X, you represent it by a bounded complex of flat modules, and then you just pull them back. And that's turns out to be a well-defined operation.
So is that, are you saying that the statement that this is fully faithful is that's an easy, but you're not saying why, or that it's obvious, or that it's hard, or I don't know if it's true? Yeah.
Yeah, sorry, I of course intended to give a proof, but I guess what I'm saying is, yeah, it's not very difficult and
but not obvious.
but not completely obvious. But yeah, so you have to use the projection formula, and it turns out that it's enough to see that if you do so.
Okay. I think maybe Sean Cotner might have given this argument on the Discord in a different context.
Great.
Sure. In which case, oh no, not quite, but close. But okay, here's a question then. Did you not say okay, and I have to go back to what you wrote above, but this does not imply that, okay, t to t prime, this doesn't imply the Rouquier dimension of y is at most the Rouquier dimension of x, because that would suck. Like that's not true.
Let's see. So
because that's not true. That's, or do I have that one?
Right. So LF upper star is the one which is fully faithful. So the lemma implies that the dimension of x is at most the dimension of y.
Oh, that's better. So you have
Which
a
is, of
P1
course,
bundle. Right.
yeah.
Okay, good. So I take back what I said about Sean proving something. That was a different thing. But if you, great. So if you have like a P1 bundle, like a PN, but like a nice family that's surjective flat, then of course the dimension is higher, but the Rouquier dimension is also higher.
Right. Exactly. Right. So yeah. So this is it's not a good application of the thing that I'm going to prove, of course. But yeah, it's an example.
But this also means that maybe this is also Peter Petrov mentioned something in the chat that also is related to this too, that the derived category of x is then sitting inside the derived category of y. Like you're remembering what y can map to in this nice way. You're remembering all the contractions somehow, which is kind of a surprising
right
thing.
Yeah, and they all appear sort of as semi-orthogonal components of the derived category of y, if you're familiar with that term. Yeah.
So so we can't see it. Like there's no It's not, may not be obviously there, but somehow.
Right.
Okay, this example, that seems like a powerful, like a neat thing. Okay, great.
Great. Yeah, and I guess I should say that in general, functors often come from Fourier-Mukai transforms. So there are lots of interesting examples where maybe you have a moduli space of sheaves, and you'll get a Fourier-Mukai transform, and maybe it'll be fully faithful. And I guess that's all I want to say about examples right now, unfortunately. But I hope that you guys maybe will ask about more examples afterward or something like that. All right, so I want to at least state the things, so state some results. So okay, so the way that I prove the thing about fully faithful functors implies that the dimension of the main theorem, right, is using the following thing. So I prove that dbco of x can be generated using all of the negative powers of some ample line bundle in at most dimension of x steps. All right. So this is when I said that I want to talk about a softer version of Orlov's conjecture. This is sort of what I meant. So we saw in the example of curves that you could just take some finite collection of powers of an ample line bundle, and then everything would be generated from those in the right number of steps. And here I'm doing that, but I'm not necessarily restricting myself to only finitely many powers. And it turns out that that's an easier thing to prove. Okay, so I just want to say then why this implies the main theorem of the talk. So so how you do it is you make this definition, which is due to my former classmate Dmitry Piroshkov. So if you have a triangulated category, then you can define the countable Rouquier dimension of T. So this is the countable so it's an inf over integers d, But this time, instead of things that you can generate from one object in D steps, you do things that you can generate from a countable set of objects in D steps. So, so it's the inf over integers D of, of D such that there exists a subset which is countable with the property that the things that you can build from S with D dollars is equal to the whole category T. Okay, so it's a natural extension, and it allows me to use a countable set of generators. Okay, does the definition make sense? All right, so yeah, so just the observation then is that theorem 1 plus a little bit of work, which is to give the lower bound, but it happens to, basically the same argument that Rouquier uses, just sort of works, implies that in our case, the countable Rouquier dimension of dbco of x is equal to the dimension of x, but with a small caveat that you have to assume that the ground field is uncountable. Okay, and maybe I can give you like, okay, so why do you have to assume that the ground field is uncountable? So actually, if the ground field were countable, if we were doing varieties over the rational numbers, then dbco of x would actually only have countably many objects. And then so that you would get that the countable Rouquier dimension is 0, which is sort of unfortunate. But as soon as k is uncountable, everything sort of works out. And that's just it's a minor technicality. Okay, and then this implies that this implies the original theorem of the talk in the same way that that Orlov's conjecture would. So if there exists a fully faithful functor, then the dimension of x is at most the dimension of y. Okay, so any questions about this?
If you permit me one naive question,
Mhm.
in which cases does the opposite hold? For x and y smooth projective varieties, dimension x less or equal than dimension of y, when we could say that there is such a fully faithful functor on the derived categories?
That's a great question. So, right.
Maybe
so this is
some
why
examples. Maybe some
Yeah.
examples, or
I
in
should
general.
of course give more examples, right? I mean, so yeah. Let me give more examples. Yeah.
Okay.
So there's probably no general result like this, right? But we did say that if you have like if your smooth projective variety happens to be like a P1 bundle over another one, then you would get such an example. But there are just like there are a number of very interesting examples like this in the literature. So let me just say, like, for example, that so there are some examples. So due to Kuznetsov, of fully faithful functors so from the derived category of a K3 surface to the derived category of a smooth cubic fourfold. Okay, so these are all going to sound like very strange without any context, but okay, but there are these like very interesting examples that come up in the in the wild somehow, and I guess there is like a general mechanism for producing fully faithful functors, which is that they're given by Fourier-Mukai transforms. So let me just say that in general, any fully faithful functor dbco of x to dbco of y is of the form. So it takes a complex k on x and it maps it to the following thing. So you sort of convolve with a given kernel. So what you do is you pull back k to the product of x and y, and then you tensor with some fixed object on the product, and then you push it forward. So this is for some for some object E in the derived category of the product. So this is a theorem of Orlov that that all fully faithful functors actually have this form. But okay, there's still this question of like, so given x and y, when is it true that you could find some E that makes this functor fully faithful? And it's very concrete actually. So so it turns out that that's if and only if, okay. So, okay, we call this functor phi E oftentimes. And it turns out that phi E is fully faithful if and only if basically the point objects think that it's fully faithful. So so some very explicit thing about this object E on the product. So if x star of OY of, okay, so I'm going to think of E as sort of a family of objects on the derived category of Y parameterized by x. So it's if and only if for any 2 points, x1 and x2 in x, this is the same thing as these other x groups. Okay, so I should say for all x1, x2 in x. Okay, so and if you think about it, this is what it means to say that Hom from phi E of a point to phi E of another point is the same thing as the Homs from, you know, from the first point to the second point. Okay, but also with these x groups. Sorry if I didn't say that well. I didn't really prepare to say that, but what I guess I mean is that it's okay. The fully faithful functors of this form are sort of very concrete. They're always given by some object on the product, and also it's sort of well understood when an object on the product gives a fully faithful functor, but still it's like there are just a lot of very like interesting specific examples of fully faithful functors, like this one where you have db co of a K3 surface to db co of a cubic fourfold. Okay, and of course I should say this has dimension, a K3 surface has dimension 2, and the cubic fourfold has dimension 4. So, I mean, it's another example where, of course, the theorem that I'm trying to prove is true. Yeah. Okay, are there any questions?
There are a bunch of questions for the end, but I don't know whether, do you mean that you're going to conclude and we can now ask you random questions or questions about this right now?
That's a good question. It's been an hour probably, right? So,
Yeah, I mean, the fact that we've been interrupting you and asking you a lot of things, I think has been really great for us. Maybe not for you, but
it's
so, okay. I mean, do you want to? I feel like you should be allowed to like conclude and say some words. And
okay.
then ask you more questions, or maybe
I would love to state one more thing. I
Sure.
guess actually.
Yes.
And hopefully it will lead to even more questions, which would be great. So. I just want to say one thing about how theorem 1 is proved, which is via another theorem, which I think is interesting in its own right. So, so I also proved this thing, theorem 2. So if you have K0, if you have a diagram like this in the derived category of X, so if these are morphisms in db co of X, with the following property. So such that on cohomology sheaves, you get sort of a zero map. So for all I, these morphisms are zero on cohomology sheaves. Okay, then the conclusion is that the composition is zero. So, okay, is zero. Let me write that a second time. Okay, and this is sort of slightly more mysterious maybe than theorem one, but it turns out to actually give a nice proof of theorem one, and I really hope.
So this is not a, wait, is this a derived? Is this a, this could be, you're not claiming that if I have a triangulated category, no, if I've, you're not claiming that this is not a general statement about triangulated categories.
Right.
So this is something in particular about coherent sheaves on X.
Right. So in particular, like
something's magical, there's some magic, and I have no idea why that comes into this. Oh, no,
Right.
oh, there's a DMX in there. Yeah.
Right.
Okay. That is wacky. Okay, great. Sorry. Yeah, I didn't mean to interrupt.
Thank you. Yeah, so that's a great point, right? So the statement wouldn't even make sense for a general triangulated category because I said something about the cohomology sheaves. So maybe if I said a triangulated category with a T structure or something, if you know what that means, maybe I could have asked a similar question. But no, this is actually something specific about DB code X. And okay, I'm sorry to kind of end.
You have a notion
yeah.
of, but now you have a notion of, right. So if I give you something which looks like the derived category of something, and I know that after, oh, it looks like Ellie is being attacked by some creature. And you know that you have a statement like this. You have a whole bunch of things that are zero on, you have a T structure. You have a zero on cohomology. That forces this map to be zero. Like that in itself is a dimensional, that feels like a dimension-like statement. Right? That's
Great.
Of X.
Exactly. Yeah, right. Okay, and I also kind of hope that someone's gonna ask like, okay, so there's this thing that whenever I explain the statement, people try to prove that actually each of these morphisms is zero. So like a first question, right, is how can you have a morphism in the derived category which vanishes on all cohomology sheaves but isn't zero? So yeah. So hopefully someone maybe will ask that or something, but I actually want to like give everyone a moment to like think about it if you haven't thought about it yet. But yeah, sorry to end on kind of a mystery. I did want to explain why theorem 2 implies theorem 1, but yeah, I'm gonna end here, I guess, and wait for questions.
Great. I guess we can now unmute. We had a question he's begged to be asked after, but we can take a break before asking the question and thank Noah for a great question provoking talk.